I'm developing a statistics in the news episode on the coronavirus, but that one's not today. This one's about marijuana and driving skills. Marijuana use and driving skills. Well, welcome to AP Statistics. And just a quick heads up, next week, there's no test, but we're going to be preparing for the Unit 7 test, which is 1 week from Monday. So let's take a look at today's episode of Statistics in the News. And over at NBC, this came out over Christmas just a couple of weeks ago. Even when sober, frequent marijuana users are dangerous drivers. Even when they're not high, researchers tested participants in a driving simulator. So Linda Carroll writes, even when sober, some heavy marijuana users are dangerous drivers, a new study suggests. The bad driving appears to be isolated to those who started using pot before age 16, researchers reported Tuesday, in drug and alcohol dependence. The theory is that early marijuana use changes the brain, leaving people more impulsive and more apt to make rash decisions. Not cool when you're driving.
It's true.
And so in the new study, which tested participants in a driving simulator, researchers from McLean Hospital in Boston, right next to Harvard University, found that sober cannabis users who started using the drug in their teens had more accidents, drove at higher speeds, and cruised through more red lights, and if you read the details of the study, hit more pedestrians in the driving simulator compared to people who had never used marijuana. So this is not Qwell, it's spelled K-E-W-L. Marijuana is the most commonly used illicit drug in the United States, but there has been relatively little research on its health effects, particularly on teen brains. Quote, this research suggests that early exposure to cannabis may result in difficulties performing complex cognitive tests. Notice, not will cause, but it might result. What is this? Is this an experiment or an observational study? Let's read further. Said co-author. So I'm hearing observational study. Said co-author Stacy Gruber, an associate professor of psychiatry and director of marijuana investigations for neuroscientific discovery at Harvard Medical School in McLean Hospital. For the gasp experiment. Who wrote this? Who wrote? Linda Carroll over at NBC News. For the experiment, the researchers recruited 28 regular heavy cannabis users, 23 males and 17 non-users whose driving abilities would be tested in this. Oh, so what they're imposing.
Oh, it is an experiment.
Participants' average age was 23. Okay, is that really imposing a treatment? Is this simulator imposing a treatment?
No, it's not.
Or is it just a tool for observation?
For observation, so it didn't actually kill pedestrians.
You see, the thing, if you're gonna be imposing a treatment, the treatment variable should be the explanatory variable. There should be different levels of the explanatory variable. If this were truly an experiment, may I suggest, Ms. Carroll, if this were truly an experiment, then we would be randomly selecting volunteers before age 16 and say, you've been randomly selected to be a cannabis user, a heavy cannabis user. Then we're going to see how your driving skills are 5 years from now. And then, oh, you've been randomly selected to be a non-cannabis user. So, and then or we could do a blocked experiment. So the question is, what is the treatment? The treatment should be different levels of the explanatory variable. We are comparing two different groups of people.
Yeah, because it wasn't like you had people and you gave them marijuana and then you said try. Because that would be an experiment because you could give them different.
That's right. If we randomly selected people, gave them marijuana, and so it's like, I mean, this study is all about the explanatory variable here is early cannabis use before age 16. And that's not what they're doing. They're not imposing different levels of that variable. So I began to think that this was a misuse of the word experiment. So then I looked at another publication. This was the Boston Globe. I mean, this is Boston, this is Harvard territory. And I looked at Dan Adams' description of the study. He never referred to it as an experiment, the research. And so this is, even in NBC, someone needs to be there shining light into the darkness.
NBC just needs a fact checker for 24/7. I'm gonna be completely honest with you.
So that concludes today's episode of Statistics in the News. Thanks for coming today, and we're done. Have a good weekend. No, actually, we forgot. There's the rest of class. So now let's move on to where we left off. Let's fast forward in the notes to the hoops problem. Hoops.
Oh, you're a baller, Mr. Rose.
Well, I mean, my wife was on the varsity basketball team at Wheaton College.
That's big.
So, and she got recruited to a Division II school for her basketball skills. I'm not real big into basketball. I like ping pong
Can you
and
dunk?
cross country.
Yes.
It's cross country.
Yes.
Mr. Rose, you're tall. Could
I'm
you ever
sorry?
dunk? Could you ever dunk?
I've never dunked. Could I dunk? You know, do I have the
Probably.
but I've just
believe
never
you.
succeeded. Speaking of success, what's the definition of success in problem 9? And it's not what you would expect, because here success is going to be, let's read, a basketball player has made 80% of, wait for it, her foul shots. Okay, so this is women's basketball during the season, assuming the shots are independent. Find the probability that in tonight's game, she, A, misses for the first time, so success is missing. Takes a while to wrap your head around that. What's the probability that she misses for the first time on her 5th attempt? So we have to launch a rocket, which means we have to check, we have to launch a probability model. So we think of models metaphorically as model rockets, CFL. It's not like a Canadian Football League, especially this weekend. We're here, this is Wheaton Academy, we're about the NFL. CFL doesn't stand for Canadian Football League, it stands for Conditions for Launch. You need to have your word picture in mind. See if you can draw the geometric word picture from memory. Try it, take a few moments. I'm gonna pause the camera while you quiz yourself. We're back. So hopefully you had 3 components of a Bernoulli trial, which are 2 possible outcomes, probably Wisconsin, or 10 little n is less than big N, independent representative sample. What is that 4th condition, friends?
Question.
What goes up here? It's a word. It's a hint. Write it down.
First.
The word first. We've got to be concerned about the first success of something. By the way, this is a geometric model that has a parameter p, so you need to give it a probability of success. And sure enough, they said, what's the probability that she, for the first time, so this is about geometric probability. Look, there's only 2 possible outcomes. Red matches red, make or miss. The probability of missing, I had to edit this because when I ran yours off, there was a mistake here. It says it makes a shot, right? Probability of making a shot. But here we're talking about the probability of missing a shot. So change making to missing in your notes and change 80% to 20%. Shots are independent of one another because making or missing a shot does not affect the probability of making the next. So
That's not true.
blue connects with blue,
Like it does.
which is a
Like
shaky
getting your-
assumption because it's kind of ignoring the dynamic
You're
of
getting your rhythm.
Mental
getting into a zone or
Yes.
getting into a slump. Sometimes, you know, especially when you're in front of a big crowd of people and you miss, like, well, so, I mean, it's debatable, because someone said, well, look, they're an 80% free throw shooter, which means, given the reality of zones and slumps, she's still an 80% shooter. Well, is it geometric model the right model? We have to assume independence to use the model, so at least we're announcing our assumption. It may be a false assumption, but this is what we're assuming if we're gonna use a geometric model. And then if there's a real mismatch between what we observe and what the model predicts, then maybe we can talk about, well, maybe we got an issue here with this assumption. But since these problems deal with shooting until the first miss, a success is defined as a miss. So the probability of success is 0.2, 0.2. And the geometric model G of 0.2 is appropriate. By the way, There is a little bit more to the word picture. There is a mean value of x, which you might recall is 1 over p. The standard deviation of the random variable, which is the number of shots until the first missed shot. Standard deviation of this random variable is q over p squared. And then remember, there is a probability of capital X equals k is failure to the k minus 1 times success. So that's the entire word picture that we're working on. I mean, we basically have 1 more week to memorize the word pictures, and depending on the extent to which you have a photographic memory, it'll be either harder or not as hard to remember these pictures. Try to make them easy to remember by making them visual. So this problem requires model, mechanics, conclusion. So the model is the G of 0.2 model. It has to be declared. Now you can declare it either with G of 0.2, which takes very little time, or you can declare it with this table. Let's practice both of these. So we write G of 0.2. Would you take a moment to see if you can fill in the following yellow highlighted cells in this G of 0.2 table? So the first cell, 2, 3, 4, 5, and the K cell. Please fill in all 6 of those cells. I'm going to pause the camera while you work. I'm going to tour the room. So first of all, Lydia, I'm going to put you on the spot. What's the probability that her first miss is on the first attempt? 0.2 is correct. Now, I want you to try one more. What's the probability that the first time she misses is on the second attempt? I would go with, well, she makes the first one, which is 0.8. She makes the first one, but she misses the second one, so it's 0.8 times 0.2. So Graham, what would be the probability that her first miss is on the third attempt?
0.8 times 0.2 squared? Or is it the opposite?
No, it's like, what's happening here in the real world is that she makes it and then she
0.8
makes
squared.
it again.
Oh, I had that. Okay, yeah.
So it's 0.8 squared times 0.2. So back to Lydia, what's the probability that her first miss is on the fourth attempt?
0.8 cubed times 0.2.
Got it. Pattern keeps going, 0.8 to the fourth over 0.2. So this last cell I asked you to fill in would be 0.8 q, that's q to the k minus 1. So 0.8 to the k minus 1 times probability of success, which is 0.2. Any questions on how to fill in this model? Okay, so model, mechanics, conclusion. Now in mechanics, we basically are representing things symbolically here. And the question is, what's the probability that she misses for the first time on her fifth attempt? So what's the probability that x takes on the value of 5? Which means all you gotta do is look at the fifth cell. We've already filled it in. It's 0.8 to the fourth times 0.2. Let's take that to the calculator. So here we go. 0.8 to the fourth times 0.2. I'm looking at 0.08192. So to what do we attribute our result? The normal model? No, we didn't fly that model. We didn't fly that rocket according to the geometric model. The probability that she misses for the first time in the fifth attempt is 0.08192. Do you have any questions?
How
Just
many
happened to.
rockets are there?
Let's see, we got the normal model. So rocket is a metaphor for model.
Yes.
Normal, geometric, binomial, capital B, and there's a chi-squared. There's a chi-squared model
So those are the 4 that we'll need to know
for the AP test.
Or what about for the thing next week, the quiz next week?
Chi-squared is not on the quiz next week. Next week's quiz is about the normal, geometric, and binomial. So there's only 3 models to choose from on next Friday's quiz, next Thursday's quiz, actually. And the test, the Unit 7 test, that's a week from Monday. All right, so are we okay on this part, part A? Let's go on to the next part, part B. What's the probability that she makes her first basket? Okay, so now we're changing the definition of success. Success is no longer missing. Now success is making a basket. So conditions for launch, look, I mean, you don't have to make a big deal about it. Look, they're Bernoulli trials. Shooting until she makes her first shot. Success is defined as a made shot. So instead of the G of 0.2 model, we're going to use a different model. We're going to fly a different rocket, so to speak. We're going to use G of 0.8. So the G of 0.8 model looks a little bit different. And symbolically, it's just G of 0.8. That's all we have to do. But since we're still learning, I do want to make sure that G of 0.8 concept is firmly in your mind. Please fill in the following yellow highlighted cells. There's 6 of them. Take a moment now to fill in these 6 cells of the G of 0.8 probability model. And I'm just going to tour the room, see how you're doing. All right, welcome back. So, Devin, would you help me out here, please? What's probably that her first basket will be on the first attempt?
0.8,
Keep going.
0.2 times 0.8, 0.2 squared times 0.8, 0.2 cubed times 0.8, 0.2 to the 4th times 0.8, and then it's 0.2 k to the minus 1 times 0.8.
0.2 to the k minus 1 times 0.8 is correct. So using this model, we want to find out that the first successful basket is on her 4th shot. Well, that's just this part of the model. We're just going to pull that up here, 0.2 cubed times 0.8. And what did you get when you typed that into your calculator? Graham, have you typed that in yet?
I have not.
You have it, Lydia, correct?
0.0064.
Less than 1%, very unlikely. But it makes sense, she's an 80% free throw shooter, so for her to miss her first 3 shots, it's pretty unlikely.
Unless she's in a funk.
Yeah, that's right, could be, she's in a slump. I guess slump is more associated with baseball, a hitting slump. Drought, sometimes they say drought. Any questions on part B? Hey, let's go to part C. So in part C, she makes her first basket. So now we're talking about first again. So we're still, it's Bernoulli trials with focus on first. Makes her first basket on one of her first 3 shots. So which model are we going to fly here, so to speak? G of 0.2 or G of 0.8? Which model do we use for part C?
Oh, G.
Yeah, we're focusing on the first successes defined as making. So let's use G of 0.8. See if you can do this one on your own. Trying to finish up this part. I'm going to pause while you work. Well, here we go. So we're using that G of 0.8 model again, filled in the same as last time. And some of you are like, you know what? I already filled it in. I know what it is, so I can refer to the previous page. The first 3 shots, it's like the first made is first, second, or third. So you're probably just adding up the first 3 cells. It's like you're finding the area under a curve, but you're just adding up 3 cells. It looks like when I toured the room, you had 0.8 plus 0.2 times 0.8 plus 0.2 squared times 0.8. And it really doesn't take all that long to type into the calculator. I mean, if I'd said, what's the probability that her first made shot is one of her first 17 shots, then you wouldn't want to have to type in the first 17 terms of this table. But we've got 0.8 plus 0.2 times 0.8 plus 0.2 squared times 0.8. So my guess is a lot of you came up with, it's like, wow, that's a big probability, like 99.20. She's that good of a free throw shooter, 0.8. I don't know what Kobe was. Was Kobe a great free throw shooter?
Kobe was a pretty good shooter.
Yeah, in general, but it's like, what's the chances that she's really gonna miss her first 3? You know, it's like, yeah, that's understandable. That would be right there. But how could I use Geomet CDF to speed this up, to reduce the number of keystrokes? Who remembers what the correct way to use Geomet CDF would be to get the same answer? Yes, go ahead.
0.8, 3.
Yeah, the probability of success is 0.8, and I need the first 3 numbers there, all the way up to 3. Same answer. So type them both in if you haven't already. I want to make sure that you remember how to locate Geomet CDF. Go ahead and show me your calculator with Geomet CDF giving you the same result. Be careful, and just rotate.
That's not $100 calculator.
This is more than $100. This is like 5,000, because I'm used to
$100 calculator.
Is that for Dan?
I guess it ended up being for Dan, because it certainly wasn't for you.
Oh.
Why are you so?
No, it was for you and Dan. All right, here we go.
Yeah.
So the conclusion is 0.92. Okay, more hoops.
More hoops.
For the basketball player in exercise 9, what's the expected number of shots until she misses? So here's the part of the word picture under the capital G where we look at mu sub x. We talked yesterday is 1 over p. Standard deviation of x is q over p squared. All right, so what's the expected number of shots until she misses? Okay, so since we've suddenly defined success as missing a shot, we're gonna fly g of 0.2. So if x represents the number of attempts, the number of shots until, and the definition of the random variable, it has to have the word first in there, until the first miss. So the expected value of that is the 1 over p formula, 1 over 0.2. And 1 divided by 1/5 is 5. So we're expecting her to take 5 shots until her first miss. They didn't ask for the standard deviation. If they did, let's just practice doing that. Standard deviation of that be q over p squared. Okay, so that would be 0.8 divided by 0.2 squared shots. And careful use of parentheses on the calculator. 0.8 divided by the quantity, 0.2 squared, is 20. So that's huge. To the first miss. Standard deviation of 20. Just was not expecting to see a number that big. So, all right, now what we're going to do is move on to our next lesson, because this is exactly what happened in my 5th period class, is we had a little bit of time left over. So we were able to get a head start on Monday's lesson. So I've got paper notes for you. Dan already got his paper notes. We're going to pause this. Okay. So Monday's lesson, which we're kind of starting today, is all about flying the binomial distribution model of x. It's a probability distribution. You can think of this as a condensed form of the title binomial probability distribution of random variable x. The binomial situation has 4 conditions, and good news, the first 3 conditions, red, green, blue, are the same as red. Basically, it's got to be Bernoulli trial, so it's got to be 2 possible outcomes. Probability of success, p is constant, or if it's not at least 10, little n is less than big N is a safety net. And the events, the trials have to be independent or a representative sample. But here the fourth condition for launching a binomial probability distribution model is a little bit different. Instead of the first success, we are looking at, here we go, wait for it, fixed. A fixed number of successes. We don't really care about the first success. We just want to know how many are there. So I'd like to give you a real world situation to help you understand when would we ever be concerned about a fixed number of successes. So I would recommend that what I'm about to show you, that you write it down. Oh, that's where we did that. Put it on like page 1. So here's a little bit of a real world situation in which we'd be concerned about a fixed number. Suppose that problem 1. The probability in a particular state, this is a deep red state politically, you've got deep red, that's Republican, deep blue would be Democrat. Suppose the probability of a pro-Trump voter being randomly selected in the state is 0.78. In fact, suppose the true proportion of Trump voters in this particular state is 0.78. Now let's take a sample of 500. Let's take 500 randomly selected and therefore a representative sample, 500 Trump voters. And what would be, well, in fact, we'll define a random variable. Let X equal, so probability, the number, it's actually it's the number of pro-Trump voters in the sample, number of pro-Trump voters in the sample of size n. That's lowercase n. So what is the expected value of X when we have a sample size of 500? Well, tell me, if you have a sample size of 500, how many would you expect there to be? How many of those 500 would you expect to be pro-Trump voters?
78 times 5.
So 0.78
390.
times 500, so 390. So you would take 500 and multiply it by 0.78, which is 390 voters. So here we're saying that it doesn't say fixed number, but it's implied. So we're not asking about how many voters do we need to poll until we find our first pro-Trump voters. No, that's not our concern. Our concern is how many pro-Trump voters are in this sample. It's like, and we could say, what's the probability that the questions will be asking, like, what's the probability that we get more than 400? That the fixed number of pro-Trump voters is 400 or more. Or we could say, what's the probability that we get exactly 392 pro-Trump voters?
Pretty low.
Yeah, I mean, any individual number would be pretty low.
That's why I said that.
But we could ask questions, we could answer questions like this using the binomial probability model. So back to your word picture, now that we have a little more knowledge of what we mean by the fixed number of successes, the mean or the expected value of X is found by taking n times p. Take the sample size times the probability of success. Now, it turns out the standard deviation of a random variable that is binomial in nature is square root of np cubed. So in this case, that would be the square root of 500 times 0.78 times 0.22. That's how you would find the standard deviation. We're not surprised that standard deviations have square roots in them. That's been before. Okay. So that's it. That's as far as we've got in fifth period. So we're going to save that.
Wow.
So I do recommend that you read chapter 17 over the weekend. We're going to continue this lesson on Monday. Have a great weekend, Dan. See you Monday.